So if it hasn't been obvious already during our discussion of the thermohaline circulation, let me just make a couple of points again, that if you look at temperatures over these regions on North America and temperatures at the same latitudes here in Europe, they are much milder here than here. This continental westerlies bring in harsh cold winters, whereas here the warm ocean, because of the Gulf Stream bringing all this heat here, makes these regions have much milder climate. Drizzle and boring weather maybe like in the UK and some parts of Germany, but essentially much milder winters than here. So the dependence of the European weather on the Atlantic meridional overturning circulation and the global thermohaline circulation has always been part of climate variability on long time scales, especially during the hominin evolution that we are looking at. So this nice figure shows you some details of the currents here in the tropics. You have trade winds blowing from east to west, dragging the ocean and creating some complicated currents, and mid-latitude westerlies dragging ocean waters this way and creating some currents as well. And for dynamic reasons, the currents on the western side of the ocean boundaries tend to be narrow, deep, and fast, as opposed to the eastern boundary currents, which are broad, shallow, and slow. So you are taking warm tropical waters north here, North Brazil current, Caribbean current, Florida current, Gulf Stream, and so on, and it has these multiple recycling systems creating the subtropical gyre, the Antilles current here, North Equatorial current, the coastal current here, the Canary current, and the Gulf Stream peels off from the coast and goes off into the North Atlantic, becomes the North Atlantic current, and then Northwest Atlantic current, the Western Weltson current, I forgot the name here, you can look it up, and Labrador current here, East Greenland current, and so on. So deep waters form here and here in the Greenland, Iceland, Norwegian seas, and this is a West Spitsbergen current here. So the conditions are favorable for deep water formation here and here, and there are northerly connections, also East Greenland current here, and Fram Strait, and the Heinrich events involve drifting of icebergs into the region from here, for example, and so on. So on long time scales, because of various reasons, when let's say during the glaciation, when the circulations change, essentially you change the Atlantic meridional overturning and you create climate changes on the western side and the eastern side, of course. So this is an example of end of Heinrich event 11. If you remember now, Heinrich events are when icebergs are drifting down and changing the salinity structure and the deep water formation here, and affecting the heat transport, because if you don't sink enough water, then you don't bring enough water to compensate in terms of mass conservation, so you don't bring as much heat northward and so on. So just briefly, coincident with meltwater event of eastern Greenland here, you get at 129.5 and 128.5 kiloyears, you had changed circulation, so a lot of cold southward currents and weakened northward currents, some with unknowns here. And marine isotope stage 5e during 128.5 to 126.5 kiloyears had slightly different currents here, with stronger East Greenland current, but you didn't have Heinrich events, so you don't have much southward drift of the icebergs, so you have stronger northward transport and different meridional overturning, which means different climates, different vegetation over here as well, different water resources, and so on and so forth. Marine isotope stage 5e cooling coincident with meltwater event of eastern Greenland at 126.5 to 125 kilo years. So you can again see the change in the current structure both from the north and from the south. So the point I'm trying to make is depending on the glacier melt number of icebergs coming in, the freshwater input into the deep water formation region would change. If you change the salinity here, evaporation cannot necessarily form heavy water if you make it very fresh, in which case you don't bring as much heat northward, which means Europe can cool down and would have affected the relatives of ours who were there at the time. So there are schematics like this based on isotopic data, protactinium, thorium data, for example, and neodymium and so on. So in the warm mode, you would have North Atlantic deep water forming and coming down south, and Antarctic bottom water coming in from the south and going back out. So this deep water formation here would prevent the Antarctic bottom water from penetrating too far north. You're going from 30 south to 60 north here. So sea ice would be less in this case in the warm mode, but when a cold mode came, you would increase the sea ice here, and you would reduce the or shift the North Atlantic deep water formation, and you would allow more of the Antarctic bottom water to penetrate northward across the equator into mid-latitudes, and you would change the entire circulation, heat transports, climates, coupled climate response, and so on. And in the off mode, when you didn't have deep water formation, then Antarctic bottom water would have to come in and get converted to surface water and go back out, and here you would have lots of iceberg discharges, which would be a Heinrich event. So Heinrich events do not occur as often as Dansgaard-Oeschger events, because there may be a threshold beyond which the flotilla of icebergs drift southward, and that doesn't happen as often. Okay, so you can also look at the related sea level changes when you have glaciations and deglaciations. Here we are again looking at 140,000 years ago to the present, looking at delta O18. So you can see the cold stadials, interstadials, Dansgaard-Oeschger events, or marine. So you have lots of those happening every 1500 years or so. So you can see that there are rapid warmings and coolings. So depending on how depleted delta O18 is, you are going into warm and cold climates. So this is from Greenland grip ice core. This is the Eemian interglacial marked here. So the warm period during the MI5, MI6 was here. MIS6 was from 160,000 years ago or so down to 135,000 years or so. 135,000 years ago, you started the glaciation that peaked at 21,000 years, but you had glacials and interglacials in the middle. So you can see this is warm here with less delta O18 depletion, and cold here during the stadial when you have cold temperatures and high depletion of delta O18. So this is using another method, and you can see similar signal here. The point of this is to look at sea level, relative sea level change. So during cold times, relatively sea level is lower. A lot of the water is locked up in glaciers. During the interglacial, you have melt off, and you get rapid increase in sea level here by as much as 130 meters, going from the minimum here to the level here, and then you have various ups and downs. So relative sea level can change by tens of meters during stadial, interstadials, and of course these are kind of just calculated as eustatic changes related to melting of glaciers, the water distributing globally over the ocean, whereas locally you get so-called isostatic changes where when you build glaciers, the land gets pushed down, and the glaciers melt, the land rises, so relatively sea level can rise and dip depending on how the land is moving locally. That's isostatic because that's local change. Eustatic is global change. So the question is always about whether marine isotope stage 2 was as cold as isotope stage 6 or not, and by all evidences isotope stage 6 was colder, sea level was lower, and remember this is the time Homo sapiens were just emerging and Neanderthals were around and so on. So by this time Neanderthals by all evidences had disappeared. So this would have created a lot of land bridges while also making the temperatures very cold, so you would have affected human migrations by a lot. So you have the thermohaline circulations being off cold and warm stages and so on, as we saw here. Okay, these are kind of schematics, but we will come back and look at this also in the modern era during the Anthropocene, when the thermohaline circulation is being perturbed by global warming, and maybe it's showing a signature in terms of a very peculiar trend in the North Atlantic where the deep water forms. So the main point of this part is that the thermohaline circulation is a big part of the global climate variability and trend, and during stadials and interstadials you had significant perturbations to the thermohaline circulation, which affected seriously the climates on North American continents and also affected the monsoons, as we will see a little bit later on, and it would have affected vegetation, fisheries and resources and so on, and living habitats for humans and other species, etc. So thermohaline circulation is a big part of climate variability at low frequencies. Heinrich events, of course, would have also brought in a lot of icebergs and affected deep water formation and the thermohaline circulation. Typically it is referred to as AMOC, Atlantic Meridional Overturning Circulation in the Atlantic, but the global part of it, as we saw before, is called the global thermohaline circulation. Okay, so just remember that every time we look at climate change, glacial, interglacials, we have to worry about how thermocline would have changed and how vegetation and other things would have changed along with that. Okay.